Okay, konnichiwa. Hello, welcome to my talk. So today we are going to talk about interpreting C extension and then turning into compiling them. My name is Benoit Daloze. I work at Oracle Labs in Zurich. I've worked on Truffle Ruby since 2014. I have a PhD on parallelism in dynamic languages. I'm the maintainer of RubySpec and Setup Ruby, and I'm also a C-Ruby committer. And Truffle Ruby, if you don't know it yet, is a high-performance Ruby implementation. It uses a GraalVM JIT compiler. It targets full compatibility with C-Ruby 3.2, including C extension, the subject of this talk, basically. And to give an example, for instance, Mastodon and Discourse can run on Truffle Ruby because of the high level of support and compatibility. It's on GitHub and so on. So why does Ruby even have C extension? What's the purpose? And there are two of them. And the first one is to bind to an existing C library. And for instance, we have like zlib, OpenSSL, MySQL, and PG. So all gem which link to the corresponding native library. And that's a frequent reason to use it. And there's the alternative, the typical one, is to use the FFI gem. And there's like about 1,000 gem using the FFI gem, but that's still like only a small portion compared to the number of C extension. And the FFI gem doesn't really work if the library uses like a lot of macro in its headers, because like you would have to replicate and copy all the logic of that in Ruby code, which doesn't feel like a good idea. And the second purpose of C extension is to improve performance, because sometimes Ruby code is too slow. And for instance, we have like JSON and message pack. They both have a C extension to speed up serialization. But this is kind of discouraged these days. You could see like this in Maxim's talk, was like it's less needed, and maybe even more so on Truffle Ruby, because you execute Ruby code so fast, like it's not that advantageous to write a C extension, and it's much higher maintenance. So far I've talked about C extension, but what I really mean is native extensions, because it's not just C, but you can also do it in C++, in Rust, and other languages. And if we look at the usage, we can see like, if we just count like a mod amongst the top 10,000 gem by number of download, if we look how many of them have a C extension, it's only 4%, which doesn't sound so much. It's like, okay, maybe this is not so important for compatibility. But if we count it correctly, so if we count it like, we count a gem having a transitive dependency on a gem with a native extension, then we see for the top 10,000 gem, it's 46% of all these gems that actually depend transitively on a C extension. And there we don't count FFI because on C-Ruby that's also a C extension, but on other Ruby implementation it isn't. So that we just don't count it as it. And we can also do like try to be a little bit more precise. So for instance, the JSON and the rack gem, they both have a pre-Ruby fallback. So they also work if C extension are not supported. But even with that, it's like still 43%. So in the end, a lot of the Ruby ecosystem still relies somehow on some C extension. And so it's important to support them for compatibility. I know that for JRuby, it's quite more complicated because there's also like JRuby extension or Java extension, and that's like more complicated to count, so I'm just not going into details here. If we look at compatibility, of course, C-Ruby is like defines the specs, so it passes everything. But Truffle Ruby, we can see like the C API specs as part of RubySpec. Truffle Ruby pass about 98% of it, so it's quite good. And of course, JRuby doesn't implement C extension, at least not in the current version, so it doesn't pass them. So I want to dig into how can we implement C extension? Like we had 10 years of Truffle Ruby, and since the beginning we wanted to implement C extension because we knew it was a key for compatibility. And we tried different approach, and there's various pros and cons to each. So I'm gonna look into some of them. And as a single little bit of background, I'm gonna explain what Truffle is. So Truffle is a framework to build high-performance languages easily. And the main gain is like you can get a JIT compiler for free by writing the interpreter. So you don't have to write the JIT compiler, you just write the interpreter and you get a JIT compiler. And the way this works, I'm not going to go into detail, but to try to get an idea, is that the GraalVM compiler, which is kind of like a language-agnostic JIT compiler, if you wish, is able to partially evaluate a Truffle language AST or bytecode, and then produce efficient machine code for it. So suppose I have a Ruby method or a Ruby block, then what's going to happen is this JIT compiler, which actually like understand only Java directly, Truffle Ruby is written in Java, so it will actually go through the Truffle Ruby interpreter and like find, okay, if there's a plus operation, I'm going to find the corresponding bytecode or node for this, and going to JIT compile that all together. And in the end, like we have machine code that's specific to this Ruby method or block. So it's as good as if you wrote a JIT compiler specifically for Ruby, but you didn't have to. And the main advantage of this, of course, you don't need to duplicate logic between the interpreter and the JIT compiler, which is something like many VMs today suffer from this problem. And then you have, of course, lots of bugs because the JIT is subtly different from the interpreter. So our story began in 2014, 10 years ago. There's an initial prototype which is using truffle-C. And truffle-C, from the name, you might guess, is a truffle interpreter for the C language. So this is quite innovative, quite unusual. Like, you wouldn't think of C as an interpreted language, but kind of we did it. And it's like, why would you do this, right? Like, what's the advantage? Why not simply using GCC or Clang? And we're going to answer this question in more detail. But here I give the highlights on this slide, which is like we want to have more freedom of representation. For instance, we can represent a C struct by a Ruby object, which sounds like quite unusual, right? Like with C struct, like just layout in memory and that's it, and a Ruby object something much more evolved, much more complicated, but we can do that. And the second reason, maybe surprisingly, is for performance. Because the GraalVM JIT compiler can compile both C and Ruby together, and so it can inline through both languages. So when we JIT compile code, typically we think, okay, we JIT compile a Ruby method, but here we can compile a Ruby method that calls a C function that calls a Ruby method. And that's a bit like on this illustration, that's what's meant. And inlining matters, right? So we have, if we look at numbers from back then, on the leftmost, we have MRI with C extension, so C Ruby, and we see it as a score of 10. And here, higher is better, and on all future graphs in the slides. And if we look on the right side, we have two bars. We have JRuby plus truffle. Well, no, it's truffle Ruby. That was the older name. But there is like with C extension and with C extension, no inline. And we see without inlining, it's about 15. So it's about 50% faster than C Ruby. But with inlining, it's something like 3 times faster, right? So this is really key to performance. And that's something also like other people have seen as well, is like when C calls Ruby, it's really slow. Ruby calling C is kind of okay, but C calling Ruby is really slow. And so with inlining, we solved this problem. So 2 years later, Sulong is started, and Sulong is the successor of truffle-C. And truffle-C parses C code, and the problem is parsing C code is quite slow, at least like compared to what Ruby would do, which is just loads some share library with the assembly already, right? So it doesn't really have to parse anything. It's more like the CPU will be the parser. And so Sulong, the difference in of parsing C code, it passes bit code, which is this intermediate representation in LLVM. And that's faster simply because of the binary format. And so Sulong uses Clang or CLang to compile from C to bit code. And then it just, so we do this step ahead of time, right? But instead of going further, instead of compiling from bit code to assembly, which Clang would normally do, we just stop there and let Sulong interpret and just time compile the bit code. And so this works not only for C, but C++ too, and anything that compile to bit code, more or less. And it's no longer a prototype because like the truffle-C was kind of like done for a research paper and like trying and experimenting. This is kind of like, okay, that's the solution we plan for some time. So let's go back to freedom of representation. So why don't we use just GCC or Clang, right? What's the advantages? And the first thing is, if we look at the Ruby headers, we can see this value type, and that's used all over the C API. And that's defined as unsigned long. So like when people talk about like, oh, people mixing pointers and integers, like Ruby does this absolutely every single time, right? And that's great, and like, okay, but like that's not convenient because you know, my objects in truffle Ruby, they are Ruby objects, which are represented as a Java object. And for a Java object, you cannot get the address. It's impossible. And the reason you cannot get it is because the GC can move it at any time, and it won't tell you about it. So if you got the address, it would already be stale, but anyway, there's no API to get it, so you just don't have the address. So you could maybe do something where like you have an extra indirection or so on, but you don't want to do that because it's more expensive, right? And so Sulong is really creative here and really powerful in that we can store the Java object into a field that's technically an unsigned long is C, but in Java, it will actually be an object field. So we have this my method. So it's a method defined in some C extension. And it takes an object, obj, and then we also alias it to foo, just for illustration. And like both of these, normally like in C, they would just be like, okay, that's just long, so just 64 bits in memory. But actually here, when Sulong interprets this, it actually has an object field or an object variable to store these things. So we can pass Ruby object directly into it. We don't need to like transform them into an integer. If we look at a second example of this freedom of representation, we can redirect access to C struct. So again, from the Ruby header, we have this struct RBasic, which like most objects use. And in that, we have the flags and the class of the object, the Ruby class of the object. And so suppose like my C extension method, suppose it tries to get the class of that object. One way to do it is to use this RBasic macro, which just return a pointer to this RBasic struct, and then read the class member. And that normally would just say like, oh, I read at offset 8 or something like this. I dereference the pointer, and I read at offset 8. And that's like rather like unflexible, right? And it's not what we want, because if you had to implement this in Truffle Ruby, then on every time you use this, you will need to allocate a native struct, which is extremely slow. And then you would like need to store the class as again an integer into it, and then that would finally support it. No, what we want is to just do all of this without native memory. And so the way this is done is actually RBasic in Truffle Ruby will not return just a native struct, it will return some kind of object. And Sulong will understand that, and when we do arrow class on it, it's gonna send an interrupt message, so a way to talk to other languages. And it will say like, hey, I'm reading member class out of this. So this is the implementation in Truffle Ruby. So we see like this RBasic macro calls this RBasic method. And this RBasic method just returns a Ruby object, which is kind of like crazy, right? Like it's supposed to return a struct, but it returns a Ruby object. And this Ruby object is kind of fairly simple, and the one thing it does is implement this polyglot read member, and then that's what will actually happen when I read the class, like in the previous, like at the top of the slide. And then you might think like, okay, but this might not be really fast, because like kind of like I'm calling from C to Ruby, and like maybe I don't have much caches or so on. But actually, because we interpret C code, we do whatever we want, right? So one typical problem I was mentioning earlier is like calling Ruby from C is really slow. And an example of that is RB phone call. So I call a Ruby method from C. So here we call the method foo on object, and we pass 0 arguments. And this normally is slow because there is no way to cache this. There's only a global cache, but you cannot have an inline cache, would be the typical optimization when you call methods. But with Sulong, we interpret, we can do whatever we want. We can have an inline cache here. And for instance, what we can do is we can inline cache the result of the method lookup. So here we can already look up the method foo and store that and like remember what class we saw. And if the next time the next object has the same class, we can just reuse that. We don't need to redo the lookup. And the lookup is expensive. Like you can think of it as one or multiple hash table lookups. Unfortunately, like this is really, really cool, but it's not quite enough. And the reason for this is like there's still some case where a Ruby object is leaked to real native memory. And one example of this is libSSL. So it's like, why would you give a Ruby object to libSSL? Like it cannot even know what it is. But the reason is like libSSL will have callback, and then you pass like both a function pointer and some data, and then this callback will receive the data, and the OpenSSL extension does this, and then passes a Ruby object like that. So at that point, we cannot, like we could try to interpret libSSL on Sulong, but it's not really a good idea. And then the next step is like, what, do we interpret the kernel? Like it's even less a good idea. So in the end, we kind of need a solution. Like what if a Ruby object really needs to go to native memory? And to solve that, we use handles. So handles are a way to associate a native pointer to a Ruby object. But we don't really like handles because they create extra indirection and extra cleanup, in general, extra overhead. Because like it's this extra indirection and to resolve this integer to the object. And so what we did initially is like to avoid too many handles is to change the extension like zlib explicitly and only create the handles where we need them. But that doesn't scale because there's so many C extensions, you cannot like modify all of them. So the solution there is like Sulong gained 2 new messages, these 2 native and as pointer. And it's a way for Sulong to say like, hey, no, I really need a native pointer or native integer to represent this object. And then at that point, it automatically asks Ruby for handle, and we create it. And so this solution is nice because it creates handles only for the case where it's like really needed and there's absolutely no way to avoid it. So let's jump to this year and let's redo everything again. So this year, I changed Truffle Ruby to run C extension natively. So we don't have Sulong anymore. And we have a set of trade-offs. We have some pros and some cons. So it's closer to Ruby because we have C or C++ code and we just compile it with Clang or GCC. So that's just the same. And yeah, we don't need to run on Sulong anymore. We still run libtruff or Ruby, but that's kind of an internal detail, just convenience and efficiency. But so what are the advantages to do this, right? The advantages is it's faster startup and warm-up, right? So the big problem before is we had all this code in C extension that we would have to JIT compile, and until it was JIT compile, it was really slow, especially compared to ahead-of-time compile code, compared to the native code that Ruby would use, right, for this C extension. And so that took a while, and also people don't really trust C compiler. So what they do is they write gigantic function with thousands of lines because they don't trust the C compiler will inline things properly. And then okay, you can try to JIT compile this, but it will take seconds. And then during seconds, your program makes absolutely no progress until this is compiled. Another reason to do this was we were able to finally run some large extension like gRPC. And this never worked on Sulong because gRPC just uses every C++ feature and weird edge cases. And so that was just there's just too many things to fix. The trade-off of this is we cannot do any magic anymore, right? So we need handles every time there's a value variable. We cannot do this lazily. And we don't have freedom of representation. If it's typed as an integer in C code, we're going to need to be an integer because that's what the processor will expect. And of course, we cannot have inlining anymore. And we cannot have inline cache inside Sulong. So that's quite a few challenges. And I'm going to go a bit about the structs here, how do we deal with that, right? So at this struct rbasic I showed earlier, is how can we support this if we run C extension natively? And the answer is basically we don't. So we could by doing the native struct allocation, which is too slow. So the idea is there's already a replacement. So you can already use rbasic class, which is a macro, and then you directly get the class without needing to have an rbasic struct in between. And so this we can just implement, there's no problem. And then for the flags, we can also have a getter and a setter. And this doesn't exist on Ruby yet, but we can add them and you can have a default implementation. But there's more struct in the C API. For instance, the RBIOT and rfile, which are both struct related to IO objects. And this we still need to support them. So what we do is when they are requested, when they are needed, we actually do a native allocation, we do a malloc, and then we set the fields, and we only support some of the fields, so we just don't define the other one, make sure they are not accessed. And so this works. It's not ideal, but it works. But this, again, there's already a replacement, and it's already deprecated pretty much. So if you want the file descriptor of an IO, you just have a function to do that. You don't need to have this struct in your hand. And one last struct is the RB encoding struct. And this is actually part of many function in the C API, so there's no way to get rid of it. But this is not that big a deal because there's 100 encodings in Ruby, so we can create 100 native struct and then call it a day. So it's not that bad. So we were saying earlier, we can't do inline caches with Sulong anymore, and that's kind of a problem because then C to Ruby call are really slow. But we found out Ruby already has kind of a notion of inline caches with macros. So if we look RB-inter normally is just a function in the C API that takes a C string and returns some kind of identifier. But here they redefine it as a macro. And they say oh, if the argument is constant, so if it's a C string literal, then we're going to do something special. Otherwise, we just call the original function. And this special thing is to use this extension block. And what happens is actually this creates a new scope in C, and it makes the whole thing an expression. So here we have this inline cache static variable, which actually is static, but inside this scope. So what it means is actually there is such an inline cache for each caller. So the two lines at the bottom actually have two different variables for them. And then if this inline cache is populated, then I just return it, and otherwise I call the original function. And so it means for these two lines at the bottom, intern foo and bar, you would think like, oh, this is slow, it's going to do a lookup every time. But no, actually there's inline cache, and this is actually as fast as if you cached it manually. So this is a nice idea, and we thought like, I think what's something we should try is to do the same for RB phone call. So we could also have an inline cache there, and like cache the method lookup that way. So the cache here, the inline cache here, would become some kind of struct, for instance, that stores the class and the method that was resolved. And then we have again like a macro, and here was going to say, okay, we declare our inline cache, and we check like, okay, if the class of the object corresponds to the class in the cache, then I can reuse my cache. And otherwise, I just use the original. I do the lookup, but also store the result in the cache. So next time, the cache will help me, hopefully. And then we go with the rest of the logic for RB phone call, which is actually calling that method. But at least we'll recache the lookup, which is like a very expensive part of it. And this is something like it's an idea. It's not been implemented yet, but it's something I hope to try soon. So in summary, we've seen that TruffleRuby started by interpreting and JIT compiling C code, and then the same but for LLVM bit code, and finally went back to compiling C code ahead of time using a system toolchain, so running C extension natively. And I want to talk very briefly about the good and the bad part of the C extension API. So the good part is this value type we saw in the beginning. It's pretty much an opaque pointer. So technically, you can use handles for it, even though this API never thought that handles would be used. So like, it's kind of like accidental, but working in a good way. And function in this API are great. We can just re-implement function differently on TruffleRuby than they are on CRuby, and that just works, no problem. Macros are a bit trickier, because if we change them, then it means we cannot reuse any precompile extension, and we have to maintain a diff on top of CRuby headers. But it's all possible. So let's go to the bad parts. So typically, the bad parts like structs. So there's still a few structs in the C API, but many of them have been removed over the years. So there's been a lot of progress there, so that's great. And then we have something like air array pointer. So this, like you call this on a Ruby array, and it gives you a pointer to objects, but like as a C representation. And so this forces a native array representation on top of your existing array representation, which is not ideal. And then, of course, force extra handles and copying and so on. And the bigger problem maybe is our string pointer, where like you get from a Ruby string, you convert to a C string. This is actually quite expensive, for instance, on TruffleRuby, because when you create Ruby string, they're actually represented in Java as a byte array. But then if you do this, then we have to copy it to a native memory, so to a native car pointer. And so this extra copy is some cost. One last thing is GC semantics. That's always trouble with like C extension API in many languages. For instance, we have the marker function for R data and R type data. That's something that CRuby GC call during the GC, which is like, yeah, if you implement this in another runtime, like on the JVM, you cannot just call random C function during the GC. It won't let you do that. So we have to emulate this somehow, and that's a bit expensive and complicated, but it is possible. And overall, this is so much better than the CPython API, because the CPython API exposes so many structs, like it's a total nightmare, and it's so bad that they are designing a new C API, basically. And even CPython developers want a new C API because they realize they can't make CPython faster, because it exposes so many internal, they can't change anything, they can't speed things up anymore. So let's talk performance. So I'm gonna benchmark CRuby tree, always use YJIT. I'm gonna benchmark Sulong, so the interpreter and JIT compiler for bitcode. And then I will have two variants. I will have something called libffi and Panama. So both of these execute C extension natively, but they have different way to call native function and to call Ruby from native function. And basically, libffi has more overhead because it's kind of more the legacy way. It goes through GNI and this libffi stuff, which is like the common library to do this kind of stuff. And Panama is kind of something new in Java that does this more directly. So instead of 2 layers, it goes through 1, basically. So let's start with something, the upcall benchmark. So this is a very small C extension. And so in this extension, I declare cfoo, so a class foo, and then I define a singleton foo method on it. And this foo method is kind of silly because what it will do is it will call itself on the receiver. So it's the same as if it returned the receiver directly. But this is on purpose. What I want to do here is like Ruby calling C calling Ruby in a very small and controlled way. And so benchmark is just calling foo.foo, and that will call the C function, which call again itself, which is defined in Ruby. And what we see there, it's like this is in million iterations per second. We see CRuby is about 18 million iterations per second, which is quite good considering what we have this RB phone call, which is quite an overhead. And on Solong, we can do this inlining, so we are quite a bit faster. They are like 42 million iterations per second. But if we run this natively, then suddenly it's very slow, right? So on libffi on Panama is so much slower, right? And this is because, yes, we don't have all this inlining anymore, so there's clearly a cost to it. And we can also see Panama is already quite a bit faster, so that's clearly the better way to do native calls. If we take something like a more realistic benchmark, like serializing JSON, we see that CRuby does about 7,400 iterations per second, which is quite good. And that's, of course, using the JSON C extension. And Solong only do 1,400. And that's a bit unfortunate and surprising that it's so much slower. But I think one of the reasons is this R-string pointer stuff. Like extra string copies kind of are pretty expensive for this extension. But then libffi is way worse. And Panama, well, is still 4 times faster than libffi, but still so far away from Solong and CRuby. But there's something else. The JSON gem also has a pure Ruby implementation. And on CRuby, that's not great, right? It's only 600 iterations per second. But with Truffle Ruby, it's 3,700 iterations per second. So that's like half the speed of C extension already like this. And then if we optimize this pure Ruby implementation in JSON, we can get to 7,800. So now we have a pure Ruby implementation that works faster than the C extension. And that's really cool. And as a note, YJIT, I think, does something like on the optimized pure Ruby version, I think it's like around 2,000 something. So it's not as fast as C extension, but it's already much better. If we look at the other side, we can try to deserialize some JSON to parse it. And then on CRuby is like about 3,000. On Solong, it's already closer, something like 2,000. On Panama, is like 1,000. And there we see like, okay, we can have a pure Ruby variant here, but like that seems harder to optimize. So like it doesn't work that well, and we would need more work to try to make it faster. But for now, it seems like the C extension is actually faster, even on Truffle Ruby. If we look at YAML.load, now we like see a completely different picture. And so part of this is like, this is measuring something different. Now we run a single iteration, and we don't have any warm-up. So we just measure the time it takes to load a 1 megabyte YAML file. And we see, yes, and some extra complexity here, like that YAML.load uses 2 things. There's psych, and there's libyaml. So psych is the C extension, libyaml is the C library that actually does the parsing, and but psych converts this to Ruby object. And so we can have many variants where we'll like run both of them on Solong, or both of them natively, or in between. And we see if we run both of them on Solong, it's really slow. So like it's only 0.14 iterations per second, so it takes like something like 7 seconds to parse this 1 megabyte file. But as we run more on native, we get faster. And that's because like, yeah, we don't need warm-up. We don't need to just-in-time compile this C function or anything. They're already pre-compiled to assembly. So that's one good advantage here of running C extension natively. If we look at Reaper, it's kind of a similar situation in that like, when running C extension natively, we are so much faster. And the reason there is like this Reaper YY parse function is like really huge. It's like 7,000 lines of code. And this is just too big to just-in-time compile. It's not reasonable. Even if we could just-in-time compile it, it would take like many seconds, maybe even a minute. And why this function is so big? Well, it's a parser generator. This is what it does. It generates huge amount of code. And there's no easy way to change it, right? So here, like running it the extension natively is a good solution, and there's not that many alternatives. Well, there's actually one alternative that Prism support now the Reaper API, so we could use that longer term. But of course, it's hardly the only C extension with big function. So in summary, it's kind of a mix, right? Like some extensions have better peak performance on Solong, but then they need a long warm-up time to get there. And some extensions are faster when run natively, and they need no warm-up at all. And we saw that Panama is so much faster than libffi, so there's really no reason to use libffi anymore. It's just like something that's very new, so we're trying to integrate it. And one more thing is there is ongoing research to actually kind of like do a bit of both automatically. So like there are some functions that would probably be worth running on Solong to avoid extra handles or to do extra inlining, but not all of it. Like if you run everything on Solong, then it's not good either, right? So this kind of boundary there to find, which is not that trivial, right? But it may be something that can be like semi-automatically guessed. So in conclusion, we saw that about 43% of the top 10,000 gems depend on a gem with native extension, so it's quite important for compatibility to support native extension. And the Ruby 6 extension API is actually not so bad and can be implemented by alternative Ruby implementation. It's not just the Ruby API, it's like something that's a bit more general than that. And Truffle Ruby first implemented it by JIT compiling C extension, which has various advantages, and then move to running them natively, which has different advantages. And in general, like in CAPI, the problem are always structs or pointers, because these leak the actual representation of things. If we have function or macro, we have much more freedom, and we can represent things differently in a more efficient manner, and can evolve the representation of things. There's some more cool things here, but I'm going to zap this slide. If you like to try Truffle Ruby, we have a recent release, and there's recently like this early access builds as well, some kind of development build. And that's it. Thank you for listening.